Let it start. Hello, people. Myself, Neeraj, and my teammates for IIFA presentation are Mohan, Vijay, and Aryaman. And now I'm going to take you through simulated annealing approach to solve curriculum-based course timetabling problem. Yeah. Now, what's the problem? This is a scheduling problem, which might seem obvious, but trust me, it's not. The scheduling problem main overview is like this. There are certain slots and there are certain tasks, and you just need to organize these tasks in those slots, but you have to satisfy some constraints, and this is where the problem comes. Now, consider I have told you that there should be we should arrange the tasks in the slots, right? Now, based on what these tasks and slots are, there are many variants for this problem, like examination scheduling problem, timetable scheduling problem, employee scheduling problem, airline scheduling problem, and etc. Now, why should this problem be solved at first? Now, there are many practical implications. Like consider the timetabling problem in IIT KGP. If there is a slow algorithm that takes half an hour, it's okay, fine, because we are going to do that only once, right? But in this case, there's not much importance. But consider the airline scheduling problem, where there are flights, there are runways, there are time slots, and there's this constraints like weather and many things, and this keeps on changing every time, and the algorithm should be so fast that it accommodates all these changes and produces the correct output. So yes, this problem should be solved very fastly, as fast as possible. It should be as efficient as possible. Now, the problem is NP complete. Like it's because consider the IIT KGP examination in some examinations which are approaching. Now, how to schedule these exams? Consider the particular course like AIFA, where there are people from other departments. Now we have to schedule AIFA examination in such a way that all the people who are attending that exam from this for this course should not have any other exams in that time slot. And still that now the brute force approach for this thing is take all the possible combinations which are exponential in nature and see whether if it works or not. Now this is a exponential algorithm. Now till now there is no deterministic polynomial time algorithm for this problem, so this problem is still NP complete as long as p equal to NP, of course. This is still a problem of concern, as I mentioned you, since there are practical implications in this airline thing. Now, to tell you how important this problem till now is, like this problem might look somewhat classical, but it isn't solved till now efficiently. That's why annually there are competitions like international timetable competitions happens every time. And to solve this particular problem, we are going to use local search to solve this efficiently. Although we are not going to solve it in polynomial time, if we do that, will be very great. We are going to do much efficient than the traditional brute force approach, and we are going to use a particular type of local search called simulated annealing approach for this thing. And now it's over to you, Mohan.
Thank you, Neeraj. Now I am going to talk about local search. I don't think I need to reiterate the importance of search. We know that search is an extremely important paradigm in AI. It is a fundamental way to even think about solving a new problem. And to solve a new problem, we first model it as a search problem and then apply one of our favorite search algorithms. Many such algorithms like DFS, BFS, uniform cost search, A star, IDA star, etc. are already taught in the class. Now, I am going to tell you about local search, which is a different way to think about search. In computer science, local search is a heuristic method for solving computationally hard optimization problems. So local search can be used on the problems that can be formulated as finding a solution which maximizes or minimizes certain criterion among a number of candidate solutions. Local search algorithms move from solution to solution in the space of candidate solutions by applying local changes until a solution deemed optimal is found or a time bound is elapsed. Here we will be interested in the optimization problems. So as soon as we look at a state, we should be able to say that this state has this much objective function. So we have an objective function, a black box given to us where we put in a state which may be a good solution or bad solution, and it tells me how bad it is or how good it is, depending on the value of the objective function. So this is the setting we are in. So just to give the final summary of local search is a mechanism which only keeps track of a single state and it doesn't worry about everything else, how it reaches there, etc. etc. It just worries about the single state and moves to neighboring states, which is why it is called local search. We are searching in the local neighborhood for the solution. And the advantages of this procedure would be that it will use very little memory. And moreover, it will scale really well in practice. No guarantees of optimal solution more often, but it will be able to find a reasonable solution in large or even infinite state spaces. As I said earlier, these are pure optimization problems. So, all states have an objective function, and our goal is to find the state with maximum or minimum objective function. Local search can be applied to different problems like vertex cover problem, traveling salesman problem, and queens, etc. Please go to the next slide. This is the pseudocode for the general local search algorithm. At first, we generate a random state which acts as an initial solution. Now we evaluate the objective function for this state and it is stored in the variable called best. Next, we take a random state in the neighborhood of the initial state and we evaluate its objective function and the result is stored in the variable called current. If current is better than best, then the new solution state is updated to present state. Finally, we iterate this process until a stop criteria is achieved. The stop criteria can be a minimal error, maximum number of iterations, etc. Finally, we return the state in the variable s as the solution when the stopping criteria is achieved. So this is in brief about the local search paradigm and its general algorithm. Now we apply one of the local search algorithms called simulated annealing with an additionally augmented feature called cutoff bound to educational timetabling problem. Please move to the next slide. Here is our problem, which is curriculum-based course timetabling problem. So the basic entities here are courses and lectures. For example, databases is the course that has been given 3 times a week. So here we have to do a weekly schedule, not for the full academic year, because we assume that it's repeated for every week. Then we have periods and days. For example, the first period on Monday is from 8 a.m. to 10 a.m. And let's say there are 5 periods per day and so on. And then we have the rooms with the number of seats. For example, NR 121 has 312 seats, NC 321 has 125 seats, etc. And then we have the curricula. Curricula means that we have, for example, CSC third year have these courses, AFA, COA, compilers, etc. And mechanical engineering third year have the courses such as heat transfer, dome, KKOM, etc. And finally, there is no enrollment because we don't compute the ROM when we do the timetable. The timetable is done before the enrollment. So it's blind in this sense. Therefore, here we satisfy the students that follow the curricula. Students that make strange choices are on their own, of course. Please move to the next slide. So these are the constraints and objectives that we call as hard constraints and soft constraints. A hard constraint is one that must be satisfied at all times. A soft constraint is a want to be satisfied as much as possible if the cost for doing so is not too great. So coming to the constraints here, the first one is conflicts based on curriculum. For example, two courses cannot be in the same period. It is a hard constraint. Second one is room occupancy. That is, two rooms cannot be occupied at the same time. It is a hard constraint. The third one is teacher availability. That is, a teacher can declare that they are not available on certain days. So if they are not available, they cannot be scheduled. It is also a hard constraint. The fourth constraint is room capacity. This is a soft constraint because the number of students is just an estimation. The next constraint is there is a minimum number of working days for teachers. So we don't want the teacher to teach all the lectures in the same day. This is a soft constraint. The next constraint is that there is an issue of compactness. So we don't want students to come for one lecture, then do nothing until the time for another lecture later on. This is also a soft constraint. Finally, there is this notion of room stability. That is, we want the courses to be given in the same room because the teachers and students get used to that room. This is also a soft constraint. Here, some simplifications that are not necessarily judicious were made just to create a standard problem. So that's all from my side. Now my friend Aryaman is going to explain how do we tackle this problem with the help of local search. Over to you, Aryaman.
Hello, everyone. So simulated annealing is different from local search, traditional local search, in a way that we have an additional parameter called temperature, which controls the degree of conservativeness we have in our search. So like hill climbing, we still identify the quality of local improvements compared to our neighbors. But instead of picking the best move, we select remove randomly, and we look at the change in the value of the objective function. If that change is negative for a minimization problem, then we move to that state. But if that change is positive, means we are going to a higher energy solution. We will not abandon that state, but we will still make that move with a probability which is equal to e to the power minus delta f by t. So as the temperature decreases, we become more conservative, and the probability of locally bad moves becomes lower. And typically, the temperature is decreased as the algorithms runs longer. So this is the algorithm. We have a search space which consists of all the solutions. Our neighborhood function, which consists of either swapping the rooms between two classes or moving the lecture somewhere else. Our cost function, which is the same as our objective function, and the parameters, the initial temperature, the final temperature, the rate of decay, the number of iterations per temperature, and our modification, which is the cutoff bound, NA. This is the number of accepted moves per iteration. So we initialize t as t0, we select a random solution, and we assign that to be our current best. Now, while the temperature T is greater than the final temperature, our loop variable ns runs through each values up to ns. We pick a random move and we look at the change in the energy. If that change is negative, we assign it always, and that is our current best. If not, we pick that move with a probability equal to e power minus delta f by t. And then we update our loop variable and decrease the temperature by a factor of a. So this continues along with our additional modification of capital Na, which is our cutoff bound, which means either if our energy has decreased or a less efficient move has been taken with a certain probability, we update the value of Na. And if a certain number of accepted moves have been found, we move to the next iteration, which can reduce the time of the algorithm in case Na is less than Ns. Please move to the next slide. So this is the same algorithm explained. So sampling is the process of picking a random move. Our acceptance rule is based on the increase or decrease of the energy in the neighboring states. Our cooling scheme here is a geometric progression. It need not always be, depending on the problem structure. A stop criterion consists of either reaching the final temperature, and for each loop, crossing the accepted number of moves or the number of iterations per temperature. So the parameters T0, Tf are the initial final temperatures, the cooling rate alpha, the number of moves per temperature, Ns, accepted moves per temperature, Na, and the ratio of our neighborhood function between either moving lectures to another classroom or swapping would be rho. And each of these hard constraints have a weight, which is in a vector h. Over to you, Vijay.
Okay, hello all. Let us try to solve this curriculum-based course timetabling problem using the algorithms that my friends have been discussing. Okay, to solve the algorithm, first we require a search space. Search space is a set of solutions, and we know that local search searches in the set of solutions. So let us consider an example of a search state. Please move to the next slide. This is an example of a search state. Consider the courses to be in rows and periods to be in columns in a matrix, and these are the allocated rooms for this course and the corresponding period. This is a search state. This is a solution. We keep on searching through these solutions. Now, what are the properties that should be satisfied by a search state? Conflict violations can be possible. There can be some conflicts, course conflicts or some other conflicts. Room occupancy violations can also be possible. Suppose consider C2 and C3. Both are having allocated room to be R1 in the same period. These can also be possible in the initial. We will finally move where these are not there in the final thing. Teacher availability violations shouldn't be there in the such state. That means if the teacher is not available, still the course is assigned. It is not possible. This is the search state that we are starting with, and we keep on searching through its neighbor and try to reach to the goal state. Go back. Fine. Now we have to define neighborhood. What is neighborhood? For this problem, we are defining two types of neighborhoods. Move lecture. Move one lecture to a new period and a new room, like moving AFA NR 121 8 to 10 to AFA NR 321 10 to 12, like this. This is a neighbor of the first one. Swapping lectures is also considered to be another neighbor, like swapping a period and room of two lectures, like NR 121 8 AFA is swapped with NR 421 ML. In this way, we are defining neighborhood. Now, what else we require? We require a cost function. Go to the next slide and next slide. So now we have to define a cost function. We know we are applying a search method to be we are applying search method. So we require a cost function. The cost function is defined to be weighted sum of hard constraints and soft constraints. Like suppose conflicts are hard constraints and room occupancy is hard constraint. We are have multiplying them with their corresponding hard weights, and minimum working days, room stability, room capacity, and isolated lectures are soft constraints. They are multiplied with their corresponding weights. Now this is the cost function. Based on this change in the cost function, we will apply the simulated annealing algorithm. So now we have defined everything. So now what is required? We require parameters to solve the problem. Let us go for parameters. Go to next slide. So now we are starting with some initial set of parameters, like starting temperature is in the range of 1 to 100, and neighborhood swap rate 0.1 to 0.9, like that. Everything is having corresponding their range. Let us start with this range. Now we are having entire set of things that are required to apply this algorithm. Now we can improve this algorithm by tuning these parameters. So let us do a experimental analysis. Go to next slide. This is the experimental analysis that we are conducting over the parameters. T naught, TVF, all these are we have known already. Now let us apply phrase tuning to this. By tuning this with set of all sample parameters against whole set of training instance, we will get a new set of parameters which can fit the model very well. By tuning, that means we are moving to best parameters than the parameters that we have defined already. So now we'll get a better set of range for the parameters, which will work very well by tuning. Let us go to the next slide. After applying this tuning technique, we are approaching to new range of parameters like starting temperature lying from 1 to 40. See, neighborhood swap rate is coming around 0.43. We are approaching very much near to the optimal thing, which can improve our algorithm very much. These are the final set of parameters that we are using for this algorithm. So our algorithm is well defined with search space, neighborhood, cost function, as well as parameters. Now we will apply simulated annealing algorithm and we can get the problem solved. Okay, let us compare our solutions with some other solutions that have been already done. Go to next slide, please. SJ is the algorithm that we are applying. Let us compare this with previously previously done algorithms like MU, LR, Eluha, Abdullah over set of instances, and let us try to compare them. See, for all the blue indicates that we are better than them in many of these. So over all instances, we are much better than the previously defined algorithms in many way. Even though it is a classical algorithm, by applying set of constraints, good constraints, and also taking by tuning parameters very well, we are approaching to a better solution and much better solution than many of these could. See, or on average, we are having 82.38, which is very well compared to all of these. Even though we might not have reached the best, but we have done very well compared to the previous algorithm. This is our algorithm. Over to you, Neeraj.
Yeah, thank you, Vijay. And now considering the comments, now this algorithm, which is local search and the specific part simulated annealing technique, might seem old-fashioned, but actually it outperforms many of the algorithms in the traditional days, in the modern days, sorry. And we can see there are further improvements in this algorithm by tuning the parameters systematically and using some statistical principles on this. So thank you guys for having patience. Yeah, thank you.